Now we're going to learn how to write half reactions. In redox reactions, oxidation and reduction always occur together. The number of electrons lost during oxidation is always equal to the number of electrons gained during reduction. Half reactions separate the overall reaction into an oxidation half reaction and a reduction half, so we can clearly see how many electrons are being transferred by each reactant. Let's look at an example where iron metal reacts with chlorine to form iron 3 chloride. On the reactant side, iron is a neutral element with an oxidation state of 0. On the product side, it becomes iron 3 plus cation, meaning its oxidation state has increased from 0 to plus 3. It's undergoing oxidation. To go from 0 to plus 3, it must lose 3 electrons, which appear on the product side of the half reaction, since oxidation is the loss of electrons. We can double check this by making sure the sum of the charges is equal on both sides of the half reaction. Fe0 on the left has no charge. On the right, we have Fe3 plus and 3 electrons, 3 negatives, which sum together to 0, confirming our equation is balanced. Now let's look at the reduction half reaction for chlorine. Chlorine starts in its elemental form as Cl2, which is neutral with an oxidation state of 0. In the product, chlorine becomes Cl- with an oxidation state of -1. Because chlorine is diatomic, we must keep the formula Cl2 on the reactant side. On the product side, we need 2 Cl- ions to account for both chlorine atoms. Since each chlorine atom gains 1 electron to go from 0 to -1, a total of 2 electrons are gained. These electrons appear on the reactant side of the half reaction because reduction is the gain of electrons. To verify, the left side has Cl2 and 2 electrons, 2-, giving a total charge of -2. On the right, we have 2 Cl- ions, also -2, so the charges are balanced. The coefficients in both the oxidation and reduction half reactions should be the lowest whole numbers possible, just like when balancing any other chemical equation. However, the number of electrons lost must equal the number of electrons gained across the entire redox reaction. In our iron and chlorine example, iron is losing 3 electrons, while Cl2 is gaining 2 electrons. These numbers aren't balanced. To fix this, we use the least common multiple of 6. We multiply the oxidation half reaction for iron by 2 and the reduction half reaction for chlorine by 3. That way we have 6 electrons being lost and 6 electrons being gained. In total, 6 electrons are being exchanged in this redox reaction between iron and chlorine. Here's a practice problem. Feel free to pause the video and work through it on your own. We're looking at the decomposition of K2O. In K2O, potassium has an oxidation state of +1. In the product, potassium is a neutral element, K0, so it's undergoing reduction. Oxygen, on the other hand, goes from -2 in the compound to 0 as O2 gas, meaning it undergoes oxidation. For the reduction half reaction, potassium ions gain 1 electron to become neutral potassium atoms. For the oxidation half reaction, oxygen starts as 2 O2- ions. Since each oxygen atom must lose 2 electrons to become part of neutral O2 gas, we need a total of 4 electrons lost. Be sure to include O2 as the product since oxygen is diatomic in its elemental form. Let's look at another practice problem. This one involves sodium reacting with iron 2 chloride. Iron goes from a +2 oxidation state in the reactant, Fe2+, to 0 in the product, meaning iron is undergoing reduction. To go from +2 to 0, it must gain 2 electrons. Sodium, on the other hand, starts as a pure element, Na0, and ends as Na+. Going from 0 to +1, which means it's undergoing oxidation. It loses 1 electron per sodium. As always, you can double check which side the electron should appear on by making sure the sum of the charges is balanced on each side of the half reaction.